Okay, in this example, you are punishing the companies who are selling who is selling content product whose content is too small, much smaller than the label information. In this case, the critical value was 2.836. It means that the product was labeled as 3 pounds, but you are punishing if the sample mean of 100 random products was smaller than 2.836. So you do not punish between 2.836 and 3. Even if the average is smaller than 3 pounds, you are not going to punish that because that much difference, smaller difference, could be a measurement error or could happen due to other random errors. But if the average out of 100 is too small like this, then you are going to punish. So punishment, and in this case, 2.82 is even smaller than this critical value, which means you have to punish this company, which means you are rejecting the null hypothesis, right? You are rejecting the null hypothesis. And so don't be confused about the direction. Always you have to check if you are doing lower tail or upper tail. So rejection, in this case, lower tail test, we consider smaller than critical value. And compare with two-tail test. So if you use two-tail test, we use 1.96 for the z-value, which is top 2.5% value. Z-value is 1.96. So critical values, and first, there are two critical values because you have to concern the bottom and the top at the same time. So lower critical value 2.804, upper critical value 3.196. And second, compare lower critical value. So the two-tail critical value was 2.804, but one tail is 2.836. The margin of error is much smaller than here. Margin of error is smaller here and larger here. So the intuition is the same. You are rejecting 5%, but in one tail case, you make all the effort only on one tail. But in two tail case, you have to split your work into both sides. So yeah, you become a little more generous on in one side. Right? So this is a simple summary of the difference. If you flip the inequality, so now we are having alternative hypothesis as mu smaller than 3. So if the actual true population mean was smaller than 3 pounds, then we are going to punish. But suppose that the other case, if you punish only when the content is greater, the mean is greater than 3, only when greater than 3, which means I don't care negative side, lower than 3. In this case, your p-value must be this way, probability greater than the top tail, upper tail, probability is the p-value, and only the upper tail is your p-value. And rejection rule for t-statistic is given by this. First, you have to use z alpha instead of z alpha over 2, z alpha, but you reject if t is greater than that. So now in our example, we considered smaller than minus z, and critical value also flips to the other side. So first, inequality changes because you are rejecting if too large, so larger than a certain value will be rejected. And also you change the sign here. When you reject on the lower tail, you have to allow margin of error below the hypothesis. But when you have upper tail test, you have to allow the margin above the hypothesis, because that side is where you're working on. So the sign also changes, the inequality direction of the inequality, and this sign changes. But it is intuitive, not that difficult, not confusing at all, I believe. Okay, and we may do everything we have done for two-tailed test. We can do type 1 error probability, for example. Remember, when we calculate type 1 error for two-tailed test, we calculated critical values first, and then calculate the probability of rejection when the hypothesis was true. And then, as a result, in conclusion, it equals the significance level, which is the same in this case. Type 1 error is the rejection of H0 when it is true. And we are going to calculate, so if you have critical value, rejection happens if X bar is smaller than the critical value. And its probability, type 1 error probability, will be alpha. I'm not going to derive the equations again. It's exactly same standardization and use the standard normal distribution table, then you are going to get alpha. If not, something is wrong. You have to get alpha. And in our example, alpha is 5%, so that is simply the critical the type 1 error probability. And remember, we calculated critical value as 2.836%, and we are going to use it for type 2 error probability. Type 2, and similarly to the two-tailed test, type 2 error probability is a little bit more involved. There is no shortcut for this, and we have to assume that what is the true mean, which is different from the hypothesis. In this case, I'm going to assume 2.9. So that means the company is making a 2.9 pounds product, but selling it as a 3-pound product. So cheating, the company is cheating and has to be punished. But you may not be able to detect this difference, and you may not punish this company by error, by mistake. That error probability is the probability of not rejecting H0 when it is wrong. And when it is wrong is when mu equals 2.9. So mu equals 2.9. So use that in the standardization. Everything else is the same. And if you calculate this, you get 73%, 73, about 74%. Okay, I'm not deriving the formula again. The equation is pretty much the same, even easier than what we have done in the last lecture. Standardization, and then you get this number. Then use the CDF, the standard normal distribution CDF. So we have done this kind of exercise a lot from chapter 6. So I'm going to skip this. Now let's think about this. So we assumed 2.9. Then what would happen to this probability when you have 2.8 instead of 2.9? Think about this. I'm going to continue in the next video. Try to answer this.